So here we're going to find the derivative of tangent of x using not the quotient rule, but using the original limit definition of the derivative of any function. So remember that we have that the derivative of some function with respect to x is defined as the limit as h becomes 0 of f of x plus h minus f of x all over h. So we're going to take this and break it down step by step. Here we're going to say f of x is tangent of x, and therefore f of x plus h is just the tangent of x plus h. But then we can use some trig identities, and remember that the tangent of the sum of angles is tangent of the first plus tangent of the second over 1 minus the product of their tangents. So our f of x plus h is that. And then that allows us to say that f of x plus h minus f of x is tan x plus tan h all over 1 minus tan x tan h minus tan of x. And that is not fun. Alright, and then we just keep processing. So we have, we'll take that second term and make it into a common denominator. So we'll have this. And that's easy enough to do, especially if we don't really care about the least common denominator, and just kind of blindly put this in like this. And then that knows that we end up with tan x plus tan h minus tan x plus tangent squared of x tan h all over this ugly denominator, which we're stuck with for a little while. Okay, and then we can say that those tangent x's combine to be 0, and we have tan h plus tan squared x times tan h over 1 minus tan x tan h. And then I might want to pull out a tangent of h. So tan h, and then I'm left with 1 plus tangent squared x over 1 minus tan x tan h, which one last thing is to recognize that that numerator, 1 plus tan squared of x, is just secant squared of x, and we have this. So f of x plus h minus f of x is now tan h times secant squared h over 1 minus tan h tan x. So we can then, of course, just divide by h to get, which really is nothing more than dividing by h. And now to get ddx of tan x, we just take the limit as h becomes 0. And from here on out, we're going to use a lot of the property that the limit of products is equal to the product of the limits. So let's break up that product. We're going to use the fact that tangent of h is sine of h over cosine of h, and so we end up with 3 products. We have the limit as h approaches 0 of 1 over cosine h, and that will be multiplied by the limit as h approaches 0 of sine h over h, which is multiplied by the limit as h approaches 0 of secant squared x over 1 minus tangent x tangent h. And to be explicit, we'll put these guys in parentheses, though it's a bit optional. And so we have the blue guy, which is the limit as h goes to 0 of 1 over cosine h, and we'll evaluate that naively by just putting h equals 0 in, and so we'll have 1 over cosine 0, which of course is 1. And then we have the green guy, the limit as h approaches 0 of sine h over h, but we established in class pretty quickly that that was 1. And then we have the red guy, which is the limit as h approaches 0 of secant squared x over 1 minus tan x tan h. But the key thing here is that all the x's are constant for this, and so all we really care about is tangent of h, but the tan of 0 is 0, so this becomes secant squared x over 1 minus tan x tan of 0. And the tan of 0, of course, is itself 0. So we have 1 times 1 times the secant squared of x over 1 minus 0 tan x. But of course, 0 times tan x is just 0, and 1 minus that is just 1, and so in the end, all of it comes out to be secant squared x, which, to remind you, is the derivative with respect to x of tangent of x via limit definitions. Done.